Welcome to lecture number 8 of module 3. In the previous lecture, that is lecture number 7, we model exciter and as well as amplifier, and in that modeling, basically in this lecture 7 and 8 we are trying to see how we can control the voltage, and already I discussed the various ways to control the voltage, the various elements those are generating and absorbing the reactive power. So in the modeling part, already we have seen the model of amplifier of the AVR loop. We also saw the modeling of your exciter, and while modeling exciter, I said that we can have a transfer function here, and that is your transfer function of exciter, that is a Ke upon 1 plus St. Please note that here there are several other limiting values, even though we have not considered this excitation saturation effect. So this is a simple model so that we can see in this lecture that we can see the performance of, you can say, static as well as the dynamic performance of this AVR loop. However, for the detailed modeling, if you are using computers etc., then you can go for all the effects, that is non-linearities, limiters as well as the saturation effect. Now another major component in this AVR loop is your generator. Now we can see here, means we model our this amplifier, we had the comparator, we model this amplifier as a amplifier gain Ka upon 1 plus Sta. Again this Ka depends upon which type of amplifier you are using. You are using the rotatory amplifier, you are using a static amplifier, then gain value is decided accordingly. And then we model your this exciter model, and we represented this Ke upon 1 plus, here this is 1 plus St, and now this is going to the field voltage of your main alternator, and then we have to model that. So the generator modeling here, as I said, in the basic diagram of your complete AVR loop, we saw that here your this armature, that is 3-phase, here it is the supplying, and the field winding which was coming here, it was rotating, and this is your basically your Vf which is coming from the exciter. So here we can write, if the current which is flowing in the field winding is If, and if we are having this winding will have, let's suppose Rf is the resistance of field winding, and this Lff is the self inductance of this winding. And if you are having, because there is some mutual coupling between the field winding and the armature winding, that I can denote with LAF, means it is the inductance between the armature and the field, that is a mutual coupling. So for this circuit we have this Vf, and we can relate with the If here with this equation, means the voltage here will be equal to your Rf If plus Lff dIf upon dt. Now we have one relation here, this excitation voltage, a voltage that is generated in the terminal. Here the internal voltage we are talking, this Ef is no doubt it is your x, that is you can say omega here, this is omega is the speed, that is 2 pi f, f is the frequency, and L is the mutual coupling between A armature and the field winding, divided by under root 2 into your change in field current. So here we have written in the difference form. Now from the previous equation here, means if you can take the Laplace transform and we can write in the difference form, we can write here the change in your Vf will be equal to your Raf plus your Lff, yes, and here I can say it is your If. So this is your equation we can write here, and already from this equation we have related that If is related with the Ef. So from there we can put this value of If from the previous equation, we can get this relation here. That relates your here, this is your the voltage of the field, and that is coming from the exciter, the armature, that is a rectifier this voltage, and that is coming to the DC to your field winding. So this is a change in the voltage. This is written in the difference form, and all we are writing the difference form to see the behavior of the system. Now whole this we can represent here, suppose Rf is multiplied here, Rf you can divide here, then Rf will be going there. So we can write this complete the transfer function here. Now why I have written TDO prime? The TDO prime is your LFF upon RF, means when your armature is open circuited, there is no current or something flowing there, then the time constant of the field here, this LFF upon RF, is called the TDO prime. If you measure the time constant, if you are ignoring this LAF effect, then it should be open your armature winding. There will be no induced current there, so we can write the time constant of the field winding here, their LFF upon RF. So it is a TDO prime. So we can represent this for your generator model, and your KF, that is again we can write here omega LAF divided by under 2 RF. Now we had the three modelings, that is your amplifier. We have now amplifier, we model exciter, and now we model the generator as well. With the help of this, basically these are the three elements in your AVR loop. So here we can now again, thus we can add this generator field here effect, your field exciter modeling, amplifier, and this is your comparator, and then we have, this reference is coming from the again this voltage that is measured here, and that is compared with your VF here, that is your reference value. This terminal voltage is going to be compared. So this is a closed loop with unity feedback. Here H1 is, normally you can say, if normally we are having here some function H, that is feedback transfer function, and in this case this H is nothing but your unity. So if we can combine completely here, and I can write this GS is nothing but the total open loop, normally it is called OL, open loop transfer function is nothing but your KA into KE into your KF divided by all these time constant, that is 1 plus STA, 1 plus STE, and here 1 plus TDO prime S. So we are having this transfer function is this one. Now the closed loop transfer function will be nothing but, here I can say this GCLS will be your GS, it is already we have written as a GS, no problem. Here 1 plus GH, H is 1, so I can write here GS. Now this is your complete your closed loop transfer function, and then here your the reference value is now coming here, and we are getting your the terminal voltage. Now for this closed loop we have to see the performance that includes your static as well as dynamic performance. And let us see here that another, normally when your generator is not loaded, then the TDO prime which we have considered, that is a TDO prime if it is not loaded, but once it is loaded, you are taking current, then that value is normally modified, the TDO at the load. Here XD is the transient time, the direct axis reactance, and here X external, and then we can, from this value we can get the TDO with the load. So the static performance means we have to go for the two performance, one is a static, another is a dynamic. First let us see the dynamic, and then we have to decide the gain, because gain is very important. That basically gains gives your information about the static error, and also that gives about your dynamic performance, whether your system is stable or not. So here again I can summarize the basic objective of this control loop, that it must regulate the terminal voltage to within required static accuracy limit, means how much we want. Suppose your reference is changed, means for example your reference is changed by X%, what is your change in your output voltage, means what is the error between these two, means if it is we are changing X% here the reference value, this must is also change X%, then you can say steady state error is 0. So we try to minimize that. This, if you are changing, let's suppose your initially it was 1 per unit, now you are changing from 1 per unit to your reference 1.5, this value here should also change to 1.05, means the difference should be changed that value. Then we can say error is 0, otherwise if there is some error, normally we go for some accuracy. It is not possible that we can go for the 0% accuracy. If accuracy is 1%, 1.001 per unit, sometimes it is desirable. We'll see why accuracy, if you are going for more accuracy, sometimes it's very tough and your system loop may be unstable. So that is one criteria. Second criteria is have sufficient speed of response, means your response should be very fast, means your settling time should be less, means your system must be settled. If there is some step change here in the Vref, here your Vref you can say change, then it must this output should be changed here and then it will be settled very quickly. And another criteria that your whole this AVR loop must be stable. If it is unstable, then it will create chaos, and then if you want to do something, it will do something else. So these are the basic criteria. Now let us see the static response, and let us say we need the accuracy of X%. X may be 0, X may be 1, X may be 2%. So here this X, now what is this X? X now we can define the final, that is your change in the V reference Y to the change in the steady state voltage of this one. If you remember here, this we had this your change in your Vref. Here this is coming your change in the voltage of your terminal voltage, and here we got the GCL, that is a closed loop transfer function. So here in steady state your output means what is the input change. So I can say it is your Y, that is a change in here as I written, that Y is change in the reference value. If you are changing certain Y component, what is the change in this value during the steady state condition? Because if you are changing suddenly, as I said, it will take some different value, but we are concerned about the steady state, and this is your called VSS we want. So this VSS input minus your output divided by input here, that should be less than or equal to X%, means X upon 100. If you want that 100, then we can say it is equal to X upon 100. But if your accuracy needs, we can say X%, means your system here error should be always less than that, or it will be equal to that value. So we want X% accuracy, so we can define this accuracy in this way. Here the change in VSS is your steady state voltage. Now let us see for our case, if we are changing the V reference, how the gain is related with this accuracy. To see this, here let us take, there is a step change in your input, means this reference you have changed here is your Y magnitude, means we have changed this suddenly Y magnitude, and this is your change in Vref. Here this is your time. So if you are taking this is a unit step input, and for that the Laplace transform if you are taking, we will get this your change in the Vref, that is a S domain, is equal to Y upon S. Your output from this equation here, this one will be equal to this reference change in the Vref multiplied by your closed loop transfer function. So here I have written this GCL multiplied by your change in Vref. So here this GCL is not EL, it is CL multiplied by Y into S, and we know this our limiting value theorem, that the final steady state value in this voltage SS will be the limit S tends to 0, S multiplied by change in Vs. Now we can see now our Ka into Ke into Kf, I have, let's suppose take as here K value. So what we are getting now, the closed loop transfer function will be, before coming here how I got it, we require this Vs in terms of these values. So what we are getting now, you remember this is your GCL, S is nothing but your GS is 1 over GS. This GS is the combined, that is amplifier, exciter as well as your generator model. So here I can write this is K upon various factors, that is 1 plus TAS, 1 plus TES, and here multiplied by 1 plus TDOS divided by 1 plus here K, again 1 plus TS, TAS, amplifier, here your this, and we are getting 3. Finally what we are getting, you can see here it is a K upon K plus, these time constants are coming into picture, means that is the TAS into 1 plus TES plus 1 plus TDO prime S. So we are getting this is your GCL. Now what we are doing, this y(s) just we are multiplying here. So this complete value we are going to write here into y upon s into s, and s tends to 0. So what happens, this is cancelled out, and all these if you are putting as 0, so this is 0, this is 0, this is 0, and finally what we are getting plus 1. So we are getting k y into 1 plus k. Here it is unity, this value is completely. So we are getting this, and now I have written here, you can remember here, this k upon 1 plus k into your y value. Now this is your VSS. Now if we are using in our definition which I defined here, that this is your accuracy, this is defined as accuracy, so I can put that value here, and then I can write y minus k upon 1 plus k into y upon y, it should be less than or equal to x upon 100 here. Now we can simplify here. What happens? This y will be cancelled out here, y. So we are getting 1 upon k plus this, and finally we can simplify here, we are getting this 1 upon 1 plus k x upon 100. So we can reverse this, means we can send this side here and this side here, so we will get this 1 plus k must be greater than or equal to 100 upon x, or I can say k must be greater than or equal to 100 upon x minus 1. Now let's suppose we are having x is equal to 1%. So how much we are getting for 1%? The k should be 99. So you can say this is this x is equal to 1%, means x is equal to 1 we are putting, and then we are getting k must be greater than or equal to 99. Now if we are going for x is equal to 2%, what is this? Is a 100 upon 2 minus 1 is a 49, so k must be greater than 49. This shows that if you want to more accuracy, your gain must be larger. You have to go for the larger gain. For example, if you are using x is equal to 0.05%, or you can say 0.1%, let us, what will be this value? This 0.1 here you are putting the 1000 minus this, so k must be greater than your 9099. So for more accuracy, gain must be larger, and then there may be possibility with the larger gain. Gain means is a gain for multiplication of all these three components, Ka, Ke and Kf. Then for the larger gain, you can see for the 0%, what happens? Virtually 0. If you are putting 0 here, this value is infinite. So you should require very large value of gain, and which is sometimes not possible. It is not possible to realize the infinite gain. So this normally, if we are going up to certain accuracy, we can say our system is statically error is 0. Now let us see our dynamic performance of this, and the dynamic performance just we have to go for. We'll see now the various criteria are there to see the dynamic performance of the system. Okay, so let us see our dynamic performance. The dynamic response here, the closed loop transfer function of this whole AVR loop can be written, again I derived also, k upon k plus 1 plus here your amplifier, it is for your exciter, and it is for your TF, or you can say right TDO prime, hardly matters, because the TF is the field winding time constant, and that is your TDO prime we have used to see the dynamic response. Normally the various criteria are there, because the gain we want to see for what value of gain our system will be stable. So to see, first one is that normally we go for Routh criteria, and the Routh criteria is basically the necessary condition, and it depends upon the characteristic equation of the system. Now what will be the characteristic equation? Here we can write now this, here this denominator of this closed loop transfer function must be 0. So we can say the characteristic equation here, the QS, here it is nothing but your k plus 1 plus TAS 1 plus STE, here 1 plus STDO prime. So this is your characteristic equation, and this if we are equating 0, and then we are going for the Routh criteria, and the Routh criteria you must know, here we write if this is of order n, although this is order 3 only. For the general, I can write here, if I am writing for xn, then we write the coefficient corresponding to n minus 1, and so on, and then finally s, and s0 means that is a constant. And we see here we form this criteria, and it see the first here the column, and that gives you the necessary condition. It is not sufficient, it is giving necessary condition. So if there is no change in the sign of the first column, no change here in the sign, means if all are negative, if all are positive, these coefficients of this first column, then it gives the absolute, then it is called absolute stability. Only the problem here, it doesn't provide the relative stability, means at what relatively your system is stable. Let's suppose you are having this is a system of boundary of stability, you are here, how far from your unstable zone? So it is not providing the relative stability, so that how much gain we can go for. Then we normally go for another one, that is a root locus technique. Root locus technique is nothing but it is the locus of roots gives the location of poles when gain varies from 0 to infinite. Means here if k changes from 0 to infinite, how the roots are varied, because the roots of here, the first criteria that here k is varying, then what happens? The root of this characteristic equation will change. Normally here the three order system is there, you can say s cube will be there, so third order system in this case is appearing. And what we can do, always this s should be here the negative plus minus some imaginary part, and I can say sub coefficient alpha, and here you can say omega. So this must be negative in all the case, but by varying k there is a possibility that this may go in the positive side and system will be unstable. So this root locus technique gives information if you are changing gain, how the roots are changing, whether they will cross to your left hand plane, S plane, or they will be in the same plane. So we can decide the gain, and it will give the relative stability as well. To see that, let us see one example. We can take the Ta is equal to time constant of amplifier is very fast, because let us take the static amplifier 0.2, the exciter time constant here 0.5, and the TDO prime let us take is unity. So if we put these values, then our characteristic equation which was here, and we can write with this value, putting this we can write this characteristic equation in this form, and you can see we are having the order 3, means we will get 3 roots of this equation. Now from here we can now see the open loop poles are this one, means for example you can see what we are getting, this 1 upon 1 plus 0.2 s for your for your amplifier. For your exciter we are getting 1 plus 1.5 s, and your generator it is 1 over 1 plus s. So poles are here when you are putting this is equal to 0. So here s is equal to minus 1, here if you are putting s is equal to minus 2, and here if you are putting 0, then we are getting s is equal to minus 5. So we are getting open loop poles 5, 2 and 1 corresponding to these 3, and then we have to draw this root locus and we will decide it. So from here what we do, first criteria is that normally here we draw root locus technique, here your S plane, here it is your 0, and then we mark the open loop poles, and the poles are denoted by x and the zeros are decided by 0. So here it will be, let's suppose 1, so I can say 1 will be here, another is your 2, I can say here the 2, and another is here 3, 4, 5, this is your 5. So it is minus 5, minus 2, and here it is a minus 1. So there are 3 open loop poles are there. Zeros are the numerator, this upper part of the characteristic closed loop, that will be that one. So here now you know there are the various rules, means root locus, and the movement of here means from once k is 0, let's suppose this k is 0, we are getting this one, and they are nothing but, if you solve, we are getting these are the loops. So when k is 0 means we are starting at this point here, k is equal to 0, here also your k is equal to 0, and this value also k is equal to 0. But we want to change k, means from 0 to infinite, then we will see how they are changing. Once k are 0, they are lying here, and it is your open loop. Now the movement here, always this the criteria says that here always if you are adding zeros and your poles, and if it is a even, then odd, then it will be going in your left hand side. So here it will be moving like this direction, here it will be moving like this direction. So this will be going in this direction, this will be going this direction. Here it will be going in the different direction, because they will be merging and they will be moving together. Now for that we normally decide, now here there will be some break even point that these pool where they will go. If you keep increasing, means there will be one point they will go somewhere else, and then what will be their point of here leaving point, that they will leave, and what will be the angles at which they will be moving. So that angle normally decided that where they will leave, it is normally decided by the plus minus 180 upon 2. It is your 90 degree, again depends upon the here number of 2, there is no zeros, so they will be leaving at the 90 degree somewhere. So the poles here, they will be moving here. Now what will be the asymptotes where the angle they will be moving? It is decided by your this point where we can draw the axis, that will be decided by all these poles divided by 3. So minus 5, minus 2, minus 1 divided by 3, and it is nothing but your minus 2.3. So that value here we are taking 2.3, and this is, and we have to now decide the angle. Angle will be the 60 degree here. So this 3 axes will be there, 2.3 here. Now this will be leaving at the 90 degree here, and then this will be changing. Here it will be the 90 degree. Now what will be this point of that where it will leave this real axis? That is basically decided by taking this delta ks by ds is equal to 0. To know this, what we have to do, we have to just differentiate this characteristic equation here, and then we will get the value of that. For that, if we are differentiating this here, means we are getting 10 del k upon del s, plus if you are differentiating with the s, here is a 3s square, plus here your 16s, plus here 17, and that is equal to 0. Here it is, this is a constant, then differentiation of s will be 0. Now we know that this value is 0, means we are getting here, this is equation, that is a 3s square plus 16s plus 17, that is 17 is equal to 0. And if you are solving here, this is a quadratic equation, and then we will get here s is equal to nothing but your minus 16 plus minus here under root, I can go for 16 square minus 12 into 17 divided by your 6, and finally we will get the value here minus 1.5, and here we will get the minus something 4 or something 3. This is not possible, only this value is the break even point where this is the breaking is leaving this one leaving point. It will be between minus 1 and minus 2, because this value is coming here, that is not true. So this is not valid, only we are getting. So they will be living here in the intermediate of these points. So it is the point here, it is your 1.5 minus here, and they will be living at the 90 degree, and finally here the movement will be like this. So this will be your root locus. By changing the k here, this is your characteristic that is going here, means this will be moving by movement of your k, and this value is going here. So k from 0, if you are increasing this one here, your loop poles is moving in this direction, other roots, 2 roots are going in this one. Now you can see once we are increasing, this is crossing your imaginary axis here, and once it has crossed, means your system will be unstable. So the value of gain here, that is your gain critical, means always your gain must be less than this, otherwise it will be unstable, unless until you are going for some compensation technique. So here we have to determine what will be the value for, let us suppose, for this time constants. To obtain this, what we have to do, we have to find the intersection of the imaginary section, and that can be done by going for here the open loop pose. Means we have to see when it is changing, and that we can use nothing but we can go for using your Routh criteria for that. And in that criteria, what we can do, we can simply form this S cube, S square, S and S naught. So to obtain the value of K, we have to go for your Routh criteria, and here we can write the again equation that we obtained, that is x3 here plus it was your 10k if you remember, plus x3 here 8x square plus 17s plus it was 10, that was equal to 0. And for this equation we can just write your Routh criteria. So x cube here is 1, your x now minus 1, the even now we are writing here, yes, now it will be 17 for the second column. Here for the second the second row of first column, it is your 8, this value square, then we are getting here 10. Now this is not only 10 because this is also constant, so we are getting our 10 plus 10k. Now S1 is now calculated from here, means we have to calculate this and then divided by that value, then we are getting here 17. Here is a simply S. This value is now, we don't have that value, so that value is calculated, and that value is calculated this multiplication of this divided by this value, and we can get that value here is your 10 plus 10k divided by your 8, and here we are getting nothing but your 10 plus 10k. Now to obtain that value, what we can do, that this value must be greater than 0, no doubt. This value here, what we do, normally this minus this value is calculated, and this value is here what we get 17. We calculate here this multiplied by this minus this multiplied by this, we are getting 10 plus 10k divided by 8, and this value will be 0 here, we are having 0, so we are getting. So what we have to see for the Routh criteria, the first column here it should be positive, and let us see when the sign is going to change. Means here we are first criteria, that here we can say 10 plus 10k should be greater than 0, here it should be greater than, all here positive, it must be positive. So here we are getting k should be greater than minus 1, and that is always true. For another condition here, from this one it should be also positive, so I can write the 17, 8 will be divided, minus here 10 plus 10k divided by your 8 must be greater than 0. Let us suppose for the 0, what the value are. 0 means we are at the axis. If it is not 0, means we are just below this imaginary axis. Here, as I said, we are the crossing. So k value if less, here if it is a positive, then we are here somewhere, but if it is 0, we are here. If it is more, means sign change and system is unstable, and we are here. So for the 0, we can calculate, this is your nothing but is multiplied by here 17 into 8, this is yours 6, 136 minus 10 k is equal to 0, or you can say is your k is nothing but 12.6. Now you can see here the gain value, if for this time constant it is more than that, then your system will be unstable. Means here you can see this value k, if more, this term will be negative. Means there will be some sign change and it will be crossing your imaginary axis. But in the static we saw for same time constant, because it was not related with the time constant gain at that time. So the k here accuracy 1%, we saw k we required 99. X is equal to 2%, we saw k we require 49 gain, and we saw x is equal to 0.1%, here k was 999. Means if you are going for more accuracy, gain is more, but here it is now may change and it may cross this. For you can say your gain is equal to, for this k we can determine what will be the accuracy as well, no doubt we can represent. So it is for the time constant gives your dynamic response, and this value decides the stability. Means you can, if you are increasing the gain more than this, you will be no doubt will get the more accuracy, static accuracy, but your system AVR loop will be unstable. Again, now we can also determine what will be the pole or root where it will be. Means here I obtained the k value, that k is here, we calculated. Now I want to know what will be the here s value, what will be the root, what will be the magnitude where it is a crossing. Means we had this characteristic, if you remember, this is and one is here crossing, here it was moving like this and going like this. So I want to know that this value of s here, and that can be obtained by the auxiliary function. Auxiliary function is nothing but what is the function here that we can form. So at this point x k we have calculated, so I can write this 8x, just below that, above that it is 0, so we have to take this auxiliary function, and that will give the system oscillation, that will also get what will be the root at that time, k is equal to your 12.6. So it is your 8s square plus, here if we are putting the value of k is equal to 12.6, here it is 136 is equal to 0, or you can say s is equal to s square is equal to your minus 17, or you can say s will be plus minus here under root 17. So we are getting the values of here s is equal to this top one is a plus j under root 17, and here it will be minus j under root 17. So we got the here root also, we got the gain also, and then we saw that both are contradictory to each other. So let us see now overall, that is your that root locus plot. This is a complete your S plane, where this is your real axis, this is your imaginary axis, and we saw that this x relates that the pole at x is equal to minus 1 upon TDO prime. This was related to your generator. Here this pole was your exciter 1 upon T pole, and this pole was for your gain. Now once the gain is moving, here are these cross points, the gain is equal to 0, that is called open loop gains. Now if you are keep on changing your gain, then the movement, as I said, it will go at A point, they will move here, it will move at A, so it is at 8 point. If you are again increasing the gain, you will reach to B point, and this will be here, it is going in this way and it is reaching here, and the system is still stable. But again, if you are increasing the gain, let's suppose C point, then your gain from B, it can cross the axis here, and then your system will be, your AVR will be unstable. So then we find that crossing here is called your critical gain crossing, and the root here that gives your oscillation, system will start oscillating even though at this point. Although it has not crossed, but your system will start oscillating, and then end up is small perturbation, small disturbance may lead your system unstable. So we have to decide our gain up to this point, even though below that, and then our system will be stable. So this is our, without any compensation technique, without any way to improve the stability of this loop. And we find that gain was very less, to 12.6, which is very less. And for this, your steady state error will be very high. So what we have to do, because the static gain, we require more gain, so we have to do some compensation, and then we can improve the stability of the loop. And that let us see what are the various ways to improve. So we observe that stability and the accuracy are conflicting. Hence, for both we use the compensator. Means we can improve the accuracy for going for higher gain. At the same time, how we can improve the stability of the loop. So the compensators that are now available here, I can say compensator. The two type of compensators are there. One is your series and another is your shunt. And no doubt we also have shunt. Basically it is nothing but it is called your feedback controllers, feedback compensation. In series we have the different types. We always, you know it is your lead compensator, it is your lag compensator, it may be your lead and your lag compensators. Again, the lead compensator here is used to improve the stability of the system. The lags here compensator is used to reduce the steady state error, and if you are using lead lag, then it will both improve your static error as well as it will improve your stability of the system. Normally the lag compensator here, it is nothing but it is some sort of, here is a resistance, here is a resistance, here is a capacitance, and this is your compensator for your lag compensator. For your lead compensator, it is nothing but it is your resistor, and then put the capacitor in parallel with this, and here it is your resistor R2, and this will give you, means this is your R1, R2, here C, here your R1 and R2, and it's C. So this is your nothing but your lead compensator, and if you are combining both, then we can get lead lag compensator. Now the feedback here, the feedback compensator is used to improve the robustness or the more stiffness to the load variation, and always we used here, we are talking about the positive feedback. So the feedback controllers are also one way. Now let us see how it can improve the system stability. For example, let us add a series phase lead compensator. Means we are using in the series, first one, and the transfer function here, let's suppose TR is equal to your 1 plus TC. Yes. Now you can remember this open loop transfer function, that was your GOC open loop. Yes, it was your K plus 1 plus STA, 1 plus your STE, and it was 1 plus your TDO prime. Yes. Now we are using the series, then it will be multiplied. Means we are having this your G open loop, and now we are using some here the TR, that is a compensator, and then we are having this loop. Normally we put this one here this side because the output here is simply voltage. So if this will be multiplied here, and now we are getting, let's suppose 1 plus TC, that is a time constant of compensator, and here. What we can do, we can set the value of this TC in such a fashion that we can cut any of our poles here. We can cancel here the open loop poles here. For example, as I said, the TE which are having here 0.5, here we had the time constant 1, and here we had the time constant is 0.2. Now if you are putting the TC is equal to is 0.5, then what will happen? This and this will be cancelled out, and if we will draw here this your root locus here, again now we are having in this plane, we are having 1, of course, this is for your TDO prime, and then we are having for your amplifier, it is your somewhere it is -5 here, -1 here. Now what will happen, if we will draw this here, we will find that the poles here, if your gains are increasing here, they will leave at the 90 degree, and we will find this type of characteristic. So after changing, it is the gain starting from K is equal to 0 here, and it is moving here, K is your infinite. So now you can say this, after doing this compensation, this is not crossing at any time this imaginary axis. So your system is always stable, even you can go for the larger value of your gain. And if you are going for your larger value of gain, you are of course the static error will be minimum. So you can see with this, using this type of compensation, there is a series lead we have used, and our system is improved and the stability is very much improved here. Another is your, let us see the feedback. In the feedback, it has also some great advantage that it is very robust, and also it provides more stiffness to the load variation. If load are changing, also there will be less effect. What here normally we do, if again I can model, this is your generator, this we are having here the 3-phase power that is taking here, and this is your field winding, and this field winding is basically coming through your exciter, here exciter, and this exciter is nothing but your 3-phase power generation, again is another alternator, and the field to this we are giving from your, here this is a field, and this field current is coming through your amplifier. If you remember, this was nothing but your change in VR here, and this field, it is your generator or alternator there, 3-phase power supply is going. Now here we have the another, basically we had the comparator, means we measured, again you remember this using the PT, this is a potential transformer, means voltage we are measuring, and this is now given to your rectifier circuit, means we are getting some DC voltage, and this DC voltage again is compared with the comparator, and then we are here getting the V reference value, and this is coming your change in E, that is error. Now here we are using some, let's suppose the series, here we are using some series sort of compensator, and this is value is coming here, and this here we are having another winding, let's suppose here, and then we are, this is related with the feedback, I can say. So here we are giving a feedback, that is here some editor, here we are adding the positive feedback here, means we are adding, this is a from this block, this is a adder you can say. Now here we are having your change in the VST, that is a some voltage is generated, thus we are taking here, and let's suppose this the winding is having R, L and M, that is mutual coupling. So I can write the change in the VR will be equal to your Ri plus your L di upon dt. Here this voltage here in this circuit, here your I is coming, we can write this, and finally we can write in Laplace form your R plus your L, yes, here I, yes, again it is changing the IS, and now this change in the VST, it is nothing but I can write this M di by dt, the mutual coupling between these two. So this VST is generated, and then we are adding together here. So again I can write this VST Laplace domain, it will be your M here, and then we can replace this value from here taking Laplace, means we can take M into your change in I, yes, and this value is here we can write, so we are getting M over R plus Ls, R, and this is your VR, or we can say here simply we are getting the KST, the gain, plus 1 upon TST, yes, and we are getting here change in the VR. So this is your time constant, and this is nothing but the TST, it is your L upon R, and your KST, it is your M upon R. So these are the gains and the time constant of this feedback, and then with this we can, if we are putting there, because TST is very small, and if we are putting, then we can also improve the stability of the system. So in total you can say this is your feedback, means we can improve the stability either using the series or with the shunt, or that is called the feedback, and we are using here the positive feedback, and it will improve. You can now put this one in this feedback, and then you can analyze, you will find your, again we can, by changing this value of MLR, we can change the feedback, because you can say this gain is directly related with your M upon R. So M, the mutual coupling we can change, we can have the winding in a such a way, R is the resistance, always the resistance is very less, because if you are putting more resistance there will be huge loss. So this is your feedback controller. Now let us come back to this whole your AVR loop, where we previously we ignored certain things, and we ignored your basically your excitation compensation techniques, and now I'll explain that. So just I discussed that we can go for series compensation, that is a lead compensator, because we have to improve the stability. Stability is the major concern for us, so we can use the series compensation. Also we can go for the feedback controllers. Always we saw the feedback how it can be done. So if you remember in our lecture number 7, we had this brushless AVR loop, and I cut the two transfer functions here, GS and your GF. Now this GS is coming from there. So this GS is nothing but it is your series compensation. If you are adding any series compensator, that is a lead compensator, then this block will be added in the series of your this transfer function, means series transfer function, your amplifier transfer function, exciter transfer function, and of course the generator field constants. So these 4 will be added. If you are using feedback and you are not using this, then you can see again I explained this feedback, that is a GF, and GF already we model that GF in that fashion. So this is your feedback, and if you are going for your feedback as well as GS, then all these two components will be appearing. As I said, the feedback is required to provide the robustness and more stiffness to the load disturbance, and always we use the positive feedback. So we can use this one along with even those series, because that improves the stability a great. We saw that even our for larger, even though infinite value of gain, very high value of gain, it is not crossing the imaginary axis, and your loop, AVR loop, will be stable. So to recap here what we did in our for the AVR loop, in our first, and that is lecture number 7, I model this your amplifier, means we saw sinks and reactive power generators, means voltage control. Here then we find various components, then we saw the AVR loop, then again we model our amplifier with this one, and I did not consider much, only I just take the first order, the transfer function, that is the amplifier gain 1 plus STA. The time constant and gain are basically depends upon which type of amplifier you are using. You are using Amplidyne amplifier, you are using a static amplifier, the gains are changed accordingly. If you are using a static, then gain can be very high, but for others it may be not so. The time constant also, if you are using a static gain amplifier, then the time constant is very less. Now, so another, just we went for exciter modeling, and then we saw the exciter, that we can have a transfer function like this Ke upon 1 plus St, and then in this whole excitation model we ignored the limiters, because this value is also having some limiters in the VR, means your VR cannot have a larger value, so we can have some limiter, and then we can of course we model this, and we ignored the saturation, because again it is a rotating type of excitation, means it is a machine saturation effect, because saturation effect will also take into the picture. So this was your transfer function here, and now what I can see, we can now this we compared now amplifier, then exciter we model, and then that's VF, which now went for your generator modeling, and this is your VF, and we came here. Normally we did not consider here the value of the limiter. As I said, we can have the limiters here, and also we can, with this limiters we can regulate the value of VR, and also we can take the saturation effect. There will be another loop in the here excitation, that is a feedback loop will be coming. Next then we model our this generator, and the generator transfer function we write here the Kf upon 1 plus St, and we had the complete loop, and then we derived the closed loop transfer function. Then what we did, we saw the static performance we saw in terms of accuracy, how much accuracy we want, and then we found that accuracy, for the higher accuracy the gain must be larger, for lower accuracy gain must be less. Then we saw the dynamic response. In that dynamic response we analyzed this closed loop transfer function, and the route criteria is one way that will give you a necessary condition, but it is not sufficient, and also it doesn't provide the relative stability information. So we normally went for the root locus technique, which gives the plot of the roots from varying gain from 0 to infinite. And then we take one example here with this one, by taking the your amplifier time constant 0.2, exciter 0.5, and TDO is 1, and then we analyze this complete, and we found that our whole this root locus is varying like this, and finally at certain value it is at certain critical gain it will be crossing, and then your system will be unstable. So we have to use some stability improvement techniques. When some compensations are required, there is a two type of compensation, whether it is a series or feedback. In series there are the various one, it is lead, lag, or lead lag together, then feedback. And the lead is used because it used to improve the stability of the system, and we also saw if one of the pole here we can cancel this, it will be here simply, it will be vertical axis and it will not cross the imaginary axis, so the system will be pure stable. We also just went for feedback loop, and then if you are using feedback, that will provide your robustness and more stiffness to your load variation, and then we can go for the combination of both type of controllers. And then here this includes the complete your AVR loop. Now in this next lecture we also discuss the various type of other facts, basically the reactive power controllers, apart from which we discussed in lecture number 7 and 8 that we will be using some sort of devices, and using the power electronic devices we can use the static VAR compensators, that is we are changing the reactance value whenever it is required, that is SVC, it is called static VAR compensators. There are other devices like StatCom, static synchronous compensators, and others like FACTS controllers we will discuss in our next lectures, how they can improve the performance of the system in terms of voltage control, for the voltage control, and also for your power flow control or improving the stability of the system. These devices are very much useful, and that we'll see lecture number 9. Thank you.